Modern engineering relies on an assumption of perfect physical balance, where the internal forces and external excitations of a system align exactly. This equation is the baseline. A linear differential operator, L, acts on an unknown function, f of x, while an excitation term, g of x, occupies the right side. Moving the excitation term establishes mathematical equilibrium. If exact, the expression evaluates to zero. This zero state defines a perfectly solved system, a theoretical point where the chosen function satisfies every requirement of the governing equation. However, the geometries and boundary conditions of the real world are often too complex for this ideal. In practical engineering, finding that exact analytical function is a mathematical impossibility. To navigate these impossible systems, we bypass the search for the exact function and construct an approximate solution instead. Relying on an imperfect approximation creates an immediate tension. We require a rigorous method to measure specific flaws. Evaluating an approximate solution requires us to look past the standard concept of error and isolate a different mathematical entity entirely. The shift from seeking analytical perfection to managing quantifiable imperfection is the dividing line between theoretical mathematics and applied numerical engineering. This equation illustrates the formal structure of our approximate solution, constructed as a series containing two distinct parts. The trial functions, shown in blue, are known mathematical building blocks that we select to form the shape of our model. The orange coefficients are the unknown variables that we must solve for to refine that shape. We take this two-part series and plug it directly into our original differential operator. Constructing this series creates the raw tool we will use to test the governing equation. When the differential operator processes this imperfect approximation, the mathematical system reacts. The equation loses its balance. Because the input is an approximation, the result no longer equals zero. This process leaves behind a mathematical remainder, a function of our independent variable. We define this specific remainder as the residue. This residue functions as the exact quantifiable footprint of our approximation's imperfection within the system. To understand how numerical methods actually work, we must recognize that the residue is a different entity than the error. Looking at them side by side reveals the problem. Error is defined as the true function minus the approximate function. The residue is the result of the operator acting on the approximation. The error equation is a dead end. Calculating it requires knowing the true function, but if we had that, we wouldn't need an approximation. The residue equation remains viable because every component is known. We have the operator, the excitation term, and the trial functions we chose ourselves. This makes the residue fully calculable. We move away from measuring error because it requires the true solution itself. We use the residue because it is built from variables we control. Once we have defined the residue, we can use it to systematically improve our approximate solution. If we graph the residue across our domain, it appears as a fluctuating wave, deviating from the zero axis where the approximation fails to satisfy the equation. To fix this, we look back at the only elements we can change, the coefficients of our series. Adjusting these coefficients directly changes the shape and intensity of the residue wave. The goal is to manipulate these coefficients until the wave flattens, hugging the zero line as tightly as possible across the entire domain. Forcing the residue toward zero is the mechanical engine of numerical solving. It is the closest we can get to a state of equilibrium. In a rare theoretical scenario where the residue wave flatlines at exactly zero, it would mean the approximation has become the exact analytical solution. Because that rarely happens in practice, our focus remains on aggressive minimization. This process of minimizing the remainder is the core of the engineering discipline known as weighted residual methods. Understanding this framework is the necessary first step before moving into advanced techniques like Galerkin or collocation methods. By squashing the residue, we control the accuracy of the model, turning an unsolvable differential equation into a precise engineering tool.